Now that we've looked at one method of solving these differential equations, these first order differential equations, right? This separation of variables method. We're going to look at a specific example to illustrate something a little quirky that can happen with differential equations. Now, I alluded to this earlier on, and as we go through and develop more ideas and more techniques, we'll see some of these again, strange things that can happen with differential equations, right? And in this video, we're going to talk about the concept of a singular solution. Not a very difficult concept by any means, but it's an important one, and it puts the concept of a general solution in a certain context, in a certain light, right? So to kind of give you a motivation for this idea, let's look at a specific, a rather simple first order differential equation. So let's consider, let's say we have dy dx. Let's say we have something like y minus 3 squared, right? So that's our first order differential equation, and it is separable. You might say, well, where is the function of x, right? I can see a function of y, but where is the function of x? Well, we can just assume that the function of x is a constant, right? So if I think of it as this product, then I can apply my separation of variables method. I'm not even going to expand this binomial. I'm just going to keep it factored, and then let's first write it in our differential form. So we have our dy is equal to the quantity y minus 3 squared and then times dx. But this is not completely separated. Even though this is a differential form, it's not the separated differential form because we have a function of y multiplying our differential of x, right? So what we need to do is to get the quantity y minus 3 squared multiplying or some multiplicative operation times our differential of y. So we need to get this factor on the left-hand side. So the easy way to do that is to divide both sides by the quantity y minus 3 squared. So then it looks like this, right? So quite easily we can separate this differential equation. Let's go ahead and integrate both sides, right? Because that's our next step. So to integrate this, formally you would do a u sub, right? I will rewrite it in a form so that we can use our power rule. And what I'll do is I'll just kind of write down what you would do for a u sub, but this is one of those simpler ones where we don't even have to justify our method, right? We're good enough at integration that we can essentially reverse the power rule, right? And come up with the antiderivative for this. But just in case you wanted to see what the u and the du would look like, this is what it would look like. So really, I mean, you're basically just replacing the inner function with u and changing your dy into du. So not a very complicated substitution problem by any means. But anyway, as we go through and we integrate this, so we're going to add 1 to our power, divide by our new power. So we'll get negative the quantity y minus 3 to the negative 1. And then on this side, we'll have our x and then our plus c. All right. So let's see if we can write this general solution in our explicit form. So first things first, let's go ahead and we can multiply both sides by negative 1, right? So, or actually, let me do this first. I'm going to take the reciprocal of both sides to get rid of the negative 1 exponent. So let me do this. So then I'll have 1 over, right, the quantity x plus c. Then I'll just put a negative in front of this fraction to get rid of the negative in front of that quantity. So then I'll have y minus 3 is equal to negative 1 over x plus c. And therefore, here is our explicit general solution. So our function is 3 minus 1 over x plus c, right? And again, so this is our general solution, and if we had an initial condition, then we could go ahead and figure out what the constant is, right? But what's interesting about this differential equation is, when you look closely at it, right? So let me kind of summarize what we just did. So here's the differential equation. dy dx is equal to the quantity y minus 3 squared. And then we got this general solution, right? And we have it in a nice explicit form. So our general solution is this family of curves. So these are our parallel curves, right? In some sense. So why did I write a 3 there? This is a C. All right. And again, so let's say I gave you this. If I gave you this, we could easily verify that if I were to differentiate this function, so if I checked my first derivative, or if I took my general solution and subtracted 3 and then squared the result, then I would get the same thing, right? So, but the thing is, if we look closely at this, we could actually have come up with a solution for this differential equation without going through the calculus. Again, calculus is good, right? It gives us this kind of set procedure to be able to kind of unravel the secrets of the differential equations, and then we come up with our solutions, right? And not just one solution. Remember, this general solution here represents infinitely many functions that satisfy this differential equation. But I could say this. By inspection, so if I look closely at the operations here, because these are not terribly difficult operations, we note that y of x equals 3, right, is also a solution. So is also a solution. Why does it work? So we have this more complicated set of functions, right, which we know, again, and this is what our process of separation of variables tells us, that all functions of this form have to satisfy the differential equation. But just by looking at what's going on here, we can see that, for instance, if I check to see if this is an actual solution to the differential equation, right? So let's verify this. So I'll do this in a different color. Let's verify my statement here. Well, if I check the left-hand side, so I'm going to use LHS for left-hand side. Well, the left-hand side I have to do calculus, so I have to take the derivative. But nothing is easier than taking the derivative of a constant function. So if my function y of x is a constant 3, then dy dx is equal to 0, right? Okay, then so that's good. So now let's check the right-hand side. Now the right-hand side doesn't involve any calculus operation. It's basically two arithmetic operations. There's a difference, and then there's a power. So if I plug what my function is, my y, right? If I plug 3 into the right-hand side, well, let's see what happens. I'll have 3 minus 3 squared, and that will be 0 squared. So that's 0. So for all values of x, right? So notice that these two are the same regardless of what x is, right? So what we've shown is that this constant function actually satisfies the differential equation. So this is kind of interesting then, right? So, what do we have here? We have our nice general solution, right, that we get by using calculus. And then we have this kind of, this other solution, I'll just call it another solution here, that we didn't really get it from a particular process, but we were able, just by observation, looking at what the differential equation is doing, to say, well, y equals 3 would also work, right? So how do we reconcile these, right? Now, if you think about it, this is a general solution. This is a particular solution. There is no constant of integration here. There's no free variable that allows me to come up with this value of 3. So the question is y of x equal 3 an element of the set of general solutions, right? So general solutions. In other words, even though we didn't obtain this solution by using calculus, it was just more intuition, right? But is it in fact one of these, right? So in other words, let me write down the general solution in using a set builder notation. So our general solution is the set of all functions y of x such that y is equal to 3 minus 1 over x plus c, where c can be any real number, right? So what this question is asking us now is not if, is, so is 3 an element of this set? Right? Is it a part of the general solution, or is it some, I don't know, strange stepchild or something? I have no idea, right? Shouldn't have said that. But anyway, so that's the question. Well, the whole idea is, remember how we go from a general to a particular, is that we have to find a value of c, right? That's what it is, right? So the question is there a value of c, right? Since c is essentially my free variable, is there a value of c that I could plug into this general solution to get this nice specific constant solution, right? So let's rephrase the question again. So is there a c such that, and then we'll write it down now, that when that 3 minus 1 over x plus c is equal to 3. In other words, and this would be for all values of x, right? So in other words, is there a way to make these two identical, essentially, right? Well, let's see if we could solve it. Let's see if we could somehow solve this equation to figure out, is there a constant that would work, right? Just kind of looking at it, it doesn't seem likely, right? But let's see. So let's subtract 3 from both sides. So this implies we have negative 1 over x plus c is equal to 0. And I think you see a problem here, because on this side we have a fraction, right, where the numerator is a constant 1, and then on this side we have a 0. I don't think there is a value of c that we could ever come up with, right, some real number that when I plug it into this side I'll get 0. Right. Well, let's continue. Let's say again we're stubborn. We're thinking, okay, maybe this might work. I'm going to multiply both sides by negative 1. That doesn't change the right hand side. And then I'm going to multiply both sides by x plus c. Right. So this means, so I'd be left with a 1 on this side, and then I'd have 0 times the quantity x plus c on this side. So that means we would end up with a contradiction, right? So in other words, there is no value of c, right, that I could plug in. So no matter which of these elements in the general solution that I use, I would never be able to produce this special solution that we were able to find, right? So really they're separate and apart, right? So it's like we have a set of functions that work, right? Infinitely many of them, but then we have a set of, just kind of a isolated, almost singular in some sense, one single function that will work. And these are the types of functions that we describe as singular solutions. They satisfy the differential equation, right? That's what the green work here is showing us, is that we do have a solution, but that solution is separate and apart from our general solution. So let's write down that definition. So if there is no value of c. Again, remember, this is our free variable. This is the constant that we choose in order, or we obtain in order to get a particular solution. But if there is no value of that constant, right? So in the solution, so in the, oh no, let me write this. So if there is no value of c, such that the general solution produces a solution, let's just say like y equals y0, right? Then y equals y0 is called a singular solution of the differential equation. So a singular solution of the differential equation, right? So now what we can say is, so again, just kind of in summary, let's say we have, I'm going to again go back and write down what we have. So we have, this was our original differential equation. Nothing fancy about it at all, fairly simple. And then what we have now is essentially two sets of solutions. So over here we have solutions of this. So this is what we call our general solution. And these are the solutions that we get via a specific process, usually involving calculus, right? So our general solutions are of this form. This was the 3 minus 1 over x plus c, again where c can be any real number. But then we now have a singular solution, right? And again, we didn't really have a specific method for coming up with it, right? But it's of this form. This is a function here, y of x equals 3, right? So, it's not good, it's not bad, it's just a property, a characteristic that some differential equations have. Not all differential equations have singular solutions. Now, in more advanced analysis courses in mathematics, you could take ideas from multivariable calculus, so Calc 3, along with deeper theory for differential equations, and you can come up with a more systematic way of identifying when a differential equation will have singular solutions, right? So that obviously goes beyond what we're doing right now, but it's just knowing what a singular solution is and being able to, like if I were to give you a certain constant function, for instance, we would know how to verify if it is a solution, right? So that's fairly easy. That's what we did earlier when we differentiated the constant and then plugged the constant into this side and checked that we get the same result. And then seeing, okay, so we got a constant solution. Is it just a special case of the general solution? Is there some value of c that will produce this function? And if there isn't, then those are the ones we classify as being singular, right? So again, little strange things that can happen with differential equations. Not good or bad, just interesting. And for more interesting things, see you in the next video.